For a fleeting moment in cosmic history, we thought we had found it. We imagined a world, just 39 light-years away, that mirrored our own. It was a place we could almost touch, a destination whispered in the halls of science as our best chance to find a twin to our pale blue dot. Its name was TRAPPIST-1e, and for years it represented a profound and tangible hope. But the universe, as it so often does, had a surprise waiting for us. The story of this world is one of myth versus reality, of a beautiful dream colliding with the hard, cold light of data. A world once hailed as the next Earth has now become a lesson in cosmic caution, reminding us that a planet's story is written in more than just its size and its distance from a star. To understand TRAPPIST-1e, we must first journey to its home. The TRAPPIST-1 system is a marvel of cosmic architecture, a tightly packed family of worlds orbiting a star fundamentally different from our Sun. The star itself, formerly known as mass J230629280502285, is an ultra-cool red dwarf. It is barely larger than the planet Jupiter and shines with a feeble reddish light, possessing less than a tenth of the Sun's mass and a tiny fraction of its brightness. Because it is so dim, its planets must orbit incredibly close to receive any significant warmth. All 7 of its known worlds would fit comfortably inside the orbit of Mercury in our own solar system, creating a celestial dance of unparalleled intimacy. In 2016 and 2017, astronomers announced the discovery of this extraordinary system. For years, TRAPPIST-1e was more than just a data point. It was a canvas for our collective imagination. Scientists and dreamers alike painted a picture of a world that could be remarkably Earth-like. The primary reason for this optimism was its position. It receives just about the right amount of light from its star to maintain a temperature that could support liquid water. Beyond its location, its size and mass were incredibly encouraging. Planets that are too large tend to become gas giants. Planets that are too small, like Mars, struggle to hold onto a substantial atmosphere. TRAPPIST-1e sits in a sweet spot. Its gravity is strong enough to likely retain a significant atmosphere, and its density is consistent with a rocky, terrestrial world. These similarities made it an irresistible target, a place where geological and atmospheric processes could have played out. Even the planet's greatest challenge, its tidal lock, was reimagined as an advantage. The excitement surrounding TRAPPIST-1e wasn't just wishful thinking. It was grounded in sophisticated computer simulations. Scientists at NASA, the European Space Agency, universities worldwide ran countless models. They fed the known data, planet size, planet mass, orbit, star brightness, star temperature, into complex climate simulators. Same programs used for Earth's weather and climate adapted for an entirely alien world. The goal: see if any scenario could produce a stable, life-friendly surface. For a long time, the results were tantalizingly positive. Key question: heat transport. On a tidally locked planet, that determines habitability. Early models, Nature Astronomy, showed atmospheres with pressure like or greater than Earth's could redistribute thermal energy. If the atmosphere had enough greenhouse gases, carbon dioxide, methane, it could trap the star's warmth. That trapped heat would be carried by planet-spanning winds from the substellar point, the hot pole, toward the terminator, the twilight zone between day and night. This moderates extremes, creating a wide, temperate band where liquid water could exist. Models also tested oceans. An ocean stabilizes climate. Water absorbs and moves heat efficiently. They gave a clear, testable hypothesis. If TRAPPIST-1e has a thick, substantial atmosphere, it is very likely to be a habitable world. Then came the moment of truth. In the autumn of 2025, after years of anticipation, a team of astronomers pointed the James Webb Space Telescope at the TRAPPIST-1 system. They focused on planet E, waiting for it to pass in front of its tiny star. As the planet transited, a minuscule fraction of the starlight filtered through its atmospheric fringe before continuing its 39-year journey to Webb's mirrors. This light carried the secrets of TRAPPIST-1e's air. The telescope's sensitive instruments captured this light and broke it down into its constituent wavelengths, creating a spectrum. This spectrum is like a chemical barcode. Different gases absorb light at specific, known frequencies, leaving behind dark lines. The team was looking for the deep, broad absorption lines that would signal a thick, water vapor-rich atmosphere, or a carbon dioxide-rich atmosphere. Such a finding would have been a triumphant validation of the climate models. It would have been the headline of the century: Webb confirms atmosphere on potentially habitable world. But the data that came back was starkly, disappointingly clear. The spectrum was almost flat. There were no significant absorption features, no deep valleys in the graph that would indicate the presence of a substantial, molecular-rich atmosphere. The results, published in a landmark paper, were unambiguous. TRAPPIST-1e does not possess the thick, cloudy atmosphere that was so central to its promise of habitability. The absence of a thick atmosphere on TRAPPIST-1e paints a grim picture of its surface. A world without a significant atmospheric blanket is a world of brutal extremes. The fundamental problem lies with the star itself. Red dwarfs, while cool and long-lived, are notoriously tempestuous, especially in their youth. They are known to unleash powerful stellar flares, sudden, violent bursts of high-energy radiation, X-rays, charged particles. Over billions of years, this relentless stellar wind can act like a sandblaster, stripping away a planet's atmosphere molecule by molecule, a process known as atmospheric erosion. TRAPPIST-1e, orbiting so close to its star, has been in the direct line of fire for its entire existence. Without a protective atmospheric shield, the surface of TRAPPIST-1e is directly exposed to this harsh radiation. Any life on the surface would be bombarded by particles that can shred complex organic molecules, making it incredibly difficult for life as we know it to emerge or survive. Furthermore, the lack of air means there is no mechanism to transport heat. The side of the planet permanently facing the star would likely be scorched. On the opposite side, the night side, would be unimaginably cold. Temperatures would plummet to hundreds of degrees below zero, locking any remaining volatiles like water, nitrogen into a permanent, miles-thick sheet of ice. Between these two extremes of fire and ice, there would be no gentle twilight zone, but rather a sharp, dramatic drop-off in temperature, creating a landscape inhospitable to any form of surface life. It is no longer a prime candidate for surface life or a potential destination for future human colonization. Just because the surface of TRAPPIST-1e is likely a wasteland does not mean all hope for life is lost. The universe is endlessly inventive, and life on Earth has shown us that it can thrive in the most unlikely of places. The focus of our scientific curiosity has now shifted from the planet's surface to its interior. Even if the atmosphere has been stripped away, the planet itself could still harbor the ingredients for life, hidden away in protected niches. One of the most compelling possibilities is the existence of a subsurface ocean, buried beneath a thick shell of ice. This idea is not pure speculation. We see examples of it in our own solar system. Jupiter's moon Europa and Saturn's moon Enceladus are both believed to have vast liquid water oceans hidden beneath their frozen crusts. The heat needed to keep this water liquid doesn't come from the sun, but from a process called tidal heating. TRAPPIST-1e is in a similar situation, caught in a complex gravitational dance with its star and its neighboring planets. This constant tidal flexing could provide enough internal energy to maintain a layer of liquid water deep underground. In such a subterranean ocean, life would be completely shielded from the harsh radiation bombarding the surface. It would be a world of total darkness, but that is not an insurmountable barrier. On the floor of Earth's oceans, far from the reach of sunlight, entire ecosystems revolve around hydrothermal vents. The story of TRAPPIST-1e is a pivotal moment in our search for another Earth. It has not ended the search, but it has fundamentally changed its direction and methodology. For years, the habitable zone was our primary guide, a simple, elegant concept based on surface temperature. We looked for Earth-sized planets in Earth-like orbits. But the lesson from TRAPPIST-1e is that this is not enough. A planet is more than its orbit. It is a complex system, fatores com a sua estrela-mãe de formas que podem fazer ou quebrar a sua habitabilidade. The star matters just as much as the planet. Red dwarfs like TRAPPIST-1 are the most common stars in the galaxy, making up roughly 75% of the stellar population. But their violent flares and intense stellar winds may make the environments around them too hostile for JWST para reter atmosferas. This has led many astronomers to shift their focus back towards stars fatores do nosso Sol, G-type stars, e estrelas ligeiramente mais frias e calmas conhecidas como K-type stars, ou anãs laranjas. These stars are much more stable than red dwarfs. They emit less harmful high-energy radiation and have a less violent history. Their habitable zones are farther out, fatores aos seus planetas mais espaço para respirar e reduzindo os efeitos destrutivos da atividade estelar e do bloqueio de maré. The TRAPPIST-1e result also underscores the absolute necessity of atmospheric characterization. It's no longer enough to just find a planet in the habitable zone. The new gold standard is to find a planet and confirm it has a substantial atmosphere. We are atmosphere hunters. While TRAPPIST-1e may have fallen from its top spot, the catalog of potentially habitable exoplanets is vast and growing. The lessons we have learned are already being applied to a new generation of candidate worlds. Our search is now more informed, and our instruments are more powerful than ever. The quest for a habitable world is a marathon, not a sprint, and there are many other promising runners in the race. Scientists are now turning their attention to other nearby systems, particularly those orbiting the quieter G-type stars and K-type stars. Worlds like Kepler-186f, located about 500 light-years away, orbit a star on the cooler end of the K-dwarf spectrum. It is only slightly larger than Earth and resides on the outer edge of its star's habitable zone. Another promising target is Proxima Centauri b, our closest exoplanetary neighbor, just over 4 light-years away. While it orbits a red dwarf like TRAPPIST-1, its proximity allows for incredibly detailed study, and we are still working to determine if it managed to hold on to an atmosphere. Furthermore, new discoveries are being made all the time. Telescopes like NASA's Transiting Exoplanet Survey Satellite, TS, are scanning the entire sky, finding new worlds every month. As of today, in late 2025, the NASA Exoplanet Archive lists over 60 potentially habitable planets, and that number is steadily climbing. Each of these worlds is a new mystery to be solved, a new opportunity to find the signs of air and water that we look for. The next steps involve a patient and systematic survey. We will use JWST, future telescopes, to observe each of these promising candidates, one by one. We will collect their light, analyze their spectra, and build a planetary census. Some will turn out to be barren rocks like TRAPPIST-1e. Others may be mini-Neptunes with crushing gas envelopes. But the odds suggest that somewhere on that list we can find a world that has the right size, the right temperature, and crucially, the right atmosphere. TRAPPIST-1 is not the next Earth, and that is perfectly all right. Science is a process of discovery and utpadan, a null result. Learning what is not there is as valuable as a positive one. This small, distant world held up a mirror to our hopes, and in return, it gave us a profound dose of reality. It taught us that the ingredients for habitability are more complex and delicate than we once thought. It showed us the power of our tools, and it transformed speculation into data, forcing us to refine our search for more successful, long-term exploration. It was not a failure, it was a course correction. The universe does not owe us a second Earth. It does not owe us simplicity. Its beauty lies in its vastness, its complexity, and its capacity to surprise us. The story of TRAPPIST-1e is a testament to that. It reminds us to remain humble in the face of the unknown and to cherish the scientific process of questioning, fatores, e aprendendo. The data from JWST did not extinguish a light, but illuminated a new path forward. It guides us toward different stars, to ask deeper questions, and to appreciate the rare preciousness of our own world. The search for life beyond Earth is one of humanity's most profound quests. It is driven by a fundamental curiosity that 是人类经验的核心. 我们是谁? 我们estamos sós? Every planet we study, a thriving water world, a barren rock, adds a piece to that puzzle. Each one helps us understand the grand cosmic context factors o nosso próprio lar. So let us continue to look up, to build our magnificent telescopes, to launch our probes, and to dream of the worlds that may await. The search goes on.